Yeah, I mean, my brother. You might not want to. You might not use the value.
How are y'all? So, a couple of things to remind you about. I'll give your exams back at the end of class. D2L under content, exam keys will be posted here, and blank exams posted here. That way you can sort of keep up with the material or go back to it if you need to. Particularly towards the final, I think a lot of people like to review that way, so blank exams there. One other thing I wanted to mention. I forgot. I forget what the high was, but no, I don't think anyone made a 100. I think the high was a 98. Maybe a 99. Don't remember. One of those two. I forgot.
Yeah, that's what I don't get.
Okay.
It's not that it's not like it's a competition or anything.
So we're moving into Chapter 8, and 2 sections from Chapter 9 will also be attached to this unit. Chapter 8 is integration techniques. So everything to help us integrate outside of use substitution. So use substitution is really the only technique that we have at this point. All of Chapter 8, except for the last section, is devoted to integration techniques. And then we'll look at improper integrals, what happens when we try to find the area close to an asymptote, for instance. And then 9.1 and 9.3 are an introduction to differential equations. 8.1 is basic approaches to integration. There's a section in Chapter 8, 8.6, that's also other integration techniques. We won't cover that because it's more or less a collection of 8.1 through 8.5, just put in the same section. The advantage of looking at these things piece by piece is that if we know, for instance, I'm in section 8.2, all of those problems are going to involve integration by parts. If I'm in 8.4, all of those problems involve this specific integration technique. But then when you throw them all together, it really gets difficult to tell which technique should I use and how should I go about this. So if you're interested in a more generic, kind of all-encompassing approach to integration techniques, you can glance through 8.6. It would probably give you some good pointers just as a general approach. On the exam, most of the problems will be use integration by parts, use trig substitution, so it will specify on the exam. So I wouldn't worry too much. As we go through these sections, hopefully the patterns will become really noticeable and clear-cut as to when to use what technique. But 8.1 is just basic approaches. So there's really no new techniques mentioned in 8.1. There's probably a couple of techniques that we wouldn't think to utilize, but nonetheless are utilized quite frequently. And here's some basic integral formulas. You should remember these. Maybe not so much inverse secant, but definitely inverse tangent and inverse sine. Those are really, really common antiderivatives. And I'm hoping you remember all of the other ones. But inverse tangent and inverse sine, they weren't terribly common up to this point. They do get pretty frequent. So the basic idea moving forward is we already know how to use the chain rule, and the chain rule is the reverse process of what?
Use substitution.
Yeah, the use substitution helps us with the integral of something involving a composition of two functions where the chain rule was utilized to take a derivative, U substitution is the undoing of that. So just a quick reminder, we've done a lot of these so far, but find the derivative of f composed with u of x. We have to take the derivative of the outer function while leaving the inside alone, and then we multiply by the derivative of the inside. So that's a generic chain rule. A specific chain rule applied to this. The outer function is sine, so the derivative of sine is cosine. Leave the inner function alone, and then multiply by the derivative of the inner function. Okay. So I hope that's straightforward at this point. We do end up mixing derivatives and antiderivatives in the next section. So it's important to keep derivatives and antiderivatives compartmentalized. So that's our U substitution. Anything that was generated by a chain rule, the derivative is undone by U substitution. So although hopefully you don't need a U substitution here, the U, as stated in this first page, that U is reserved for the inner function. So our inner function here is 5x. du is 5 dx. And we don't have a 5 in that function, so we put that with the du. 1/5 du is dx. We have the antiderivative of sine u, and our 1/5 du for the dx. So the antiderivative of sine is what? Yeah, negative cosine. Because the derivative of negative cosine gives us sine. Be careful with your constants. Many of you forgot them. I didn't tick off for it, but it becomes crucial when you're dealing with differential equations to put those constants, because they're absolutely necessary. Okay, so we've got a negative 1/5 cosine of u, which was 5x. You know, this, let's call that C1, multiply by 1/5, we get some other constant, we'll call it C. So that's how we reverse a chain rule.
You don't distribute that 1/5?
Yeah, we distributed the 1/5 to this constant 1.
Oh.
So we just called that constant. In 8.2, we look at the technique that undoes the product rule for us. All right, so the antiderivative of 1 over x to the negative 1 plus x to the negative 3. Perhaps I should have. Should this
So how do we know which one to use?
do what?
Which of those forms to use?
Forms?
Yeah,
So those are just basic formulas. Those would show up as in conjunction with these problems. So like after we manipulated some of these, we might end up with a familiar integral from table 7.1. But example 4 is relevant to example 1. So improper fractions, you've got to remember if the degree of the numerator is larger than or equal to the degree of the denominator, there are improper fractions, and we have to divide those out. I mean, you don't have to, but typically that's the strategy. So I probably should have put this in a later example, but so it first says multiply by a form of 1 to create a function that's possible to integrate. So right now we don't recognize that as a known antiderivative.
Is this one similar to the inverse or the arctan?
No, because arctangent is the antiderivative of some number squared plus x squared. So the form of 1 to multiply this through by, multiply this by a form of 1, and we want to think about these negative exponents. Well, so if I multiplied through by x minus 1 plus x to the minus 3, sorry, x to the negative 1, if I multiply by this form of 1, then I have an even more complicated denominator, right? Because then I have their cross terms. What if we what?
Yeah, use the conjugate.
Okay, so I mean we could definitely look at that. So here's the thing with integration. With derivatives, you had rules. So no matter what kind of function you were dealing with, it said find the derivative of this, and you recognize, oh, that's a chain rule involving trig functions. I can find the derivative, right? There's always a rule to follow. With antiderivatives, it's not the case. It's not a clear-cut thing like, oh, it involves this, I should do this. It's not that simple. So a lot of these might be just trial and error. Let me try something. If it doesn't work, reformulate. So this, multiply by this. Is that what was suggested? Okay, so we don't know if that's going to work or not, but there's no reason to believe it shouldn't work. Let's just try. Oops, sorry. Okay, and what would the denominator be then?
X to the negative 2 minus x to the negative 6.
Does that look better? Looks worse.
I can try.
Yeah, I mean, there's nothing wrong with trying.
Could you multiply by x over x, and then x to the first would become 1? Or x to the negative 1 would become 1?
So multiply by
X over x.
x over x. All right, that's on the right track. Let's see what happens here. That's x over 1 plus x to the negative 2. Is that something we could work with?
It's getting better.
A little bit better.
We could try x cubed over x cubed.
Yeah, x cubed over x cubed. Let's see what happens there. X cubed over x cubed. Is that better?
Yes.
I mean, it looks better. The question is does it yield itself to something we can take the antiderivative of?
That kind of just looks like arctangent.
It kind of looks like arctangent, but we've got the x cubed on top.
So could you just multiply x cubed by
What do you mean? What would that look like?
so x squared times arctangent?
Like this?
Yeah. Is that
Where would we would multiply this in here? Or that's what that would be? What are you thinking? Oh, okay. Nazim, did you have a?
Nah.
Okay. Well, so this, maybe at this point we don't recognize that, but refer back to example 4. If the degree of the numerator is greater than or equal to the degree of the denominator, then it's an improper fraction and we have to divide. So that's exactly what we're looking at. X cubed over x squared, it's improper. So So when we divide x cubed by x squared plus 1, what's the quotient going to be? What kind of function would the quotient be?
Just X.
Yeah, it's going to involve x. It's going to be a linear thing. So you remember how to do long division?
I remember.
So we look at this term, and then we look at the divisor, or the dividend. So x squared multiplied by what will give me the x cubed? X. Okay, then what do we do with that?
And you multiply x to your x squared plus 1.
Right, then this x gets multiplied by our divisor. X times x squared is x cubed. X times 1 is x. And then what do we do with those?
Subtract.
Yeah, you have to subtract those. We subtract that, we subtract that. 0, we have a minus x. And then we start the process over if applicable. X squared will not go into x, right? So we know that this is telling us what?
We have a remainder.
Yeah, so in other words, by long division, this integral would equal to what?
X minus x over x squared plus 1.
Yeah, so we have our quotient, our remainder over the divisor. Okay, now neither one of these are improper anymore. We can certainly find the antiderivative of x. How about the antiderivative of x over x squared plus 1? Yeah, use substitution, because the derivative of x squared plus 1, a constant multiple anyways, is right here.
Just a quick question. So, because we have a dx on top of the original problem, does that mean when we have to do multiple one, it has to be a form of x? Like, is there a way we can do it to where we have dx equals 1? We have 1 over x, -1 plus x to the -3.
Without a dx?
Yeah. Like, is there a way to have dx equal 1, or is it impossible? It has to be, you have to multiply it in a form of 1, but in values of x.
Yes, right, in terms of x, yeah. Yeah, you need that dx there.
Okay.
Yeah, otherwise the integral doesn't make sense.
So I was just thinking, oh, that'd be an actual 1.
Yeah,
It was 1.
yeah. You can't do integration as we know it without that measure.
Okay.
It's a measurement on the x-axis. It's a linear measurement on the x-axis. Yeah, if you go into like higher math classes, you'll look at how do we integrate with respect instead of a line? How do you integrate with respect to like a curve or a circle, or how do you even integrate with respect to a function? But that's like different stuff.
How many years?
Huh?
How many years away is that?
I don't know. Depends on what college you go to. It could be undergrad, it could be grad. Just depends. But yeah, does everybody see that that's okay to integrate now? This one's easy. This is a U substitution. Okay. All right, so let's just break this up. Integral of x dx minus the integral of x over x squared plus 1 dx. So our u is x squared plus 1. And there's a pattern here to these types of things that we're going to point out. Once you notice them, it's going to make integrating things like of this form a lot simpler, I think. So du is 2x dx. We'll put that over here. So then we have to add in that 1/2. I'm just going to leave all of this until we're ready to integrate both. So we've got our 1/2 du for our x dx, and then this turns into 1 over u, the integral of 1 over u rather. Okay. we have antiderivative of x squared over 2, minus 1/2. What's the antiderivative of 1 over u? What is it? Yeah. It's kind of close.
Log of the absolute value.
Yeah, absolute value. And then honestly, that's kind of just know that we've got two. If we break it up, we're going to have two constants of integration that we can combine to that single constant. And then we resubstitute u x squared plus 1. We have x squared over 2 minus 1/2 ln, the absolute value of x squared plus 1 plus c. Do we need the absolute value there?
So did that one have to be applied to both, for x dx and as well as the substitution?
Well, the u substitution was this 1/2 here. This is just the power rule here. So yeah, I mean, we could take a 1/2 out, yeah. Do we need the absolute value there? No, why not? Yeah, because x squared plus 1 is always positive. No, I don't know that this is a necessary step, but you know, why deal with the absolute value if you have to? Sort of redundant. That's our answer. So then, of course, the nice thing with integration as opposed to derivatives, there was no way to check your work with derivatives, right? You just had to hope you did everything right. With antiderivatives, we can check. If I take the derivative of this, I should end up with the function I started with. Maybe not explicitly once we take the derivative, we might have to combine like terms or simplify things a little bit, but we can check, does the derivative of this equal to 1 over x to the negative 1 plus x to the negative 3. Okay, do y'all have any questions on that? Yeah.
So in this process, is long division inevitable, like, or is there something that you can multiply it by and getting to where you want to do that?
I think it's you can't avoid it here. In many instances, you can't avoid it.
Okay.
So, yeah, because you know, I don't think we multiplied through by x, and we had what, x over 1 plus x to the negative 2. You know, that's even more like improper because we still have those negative exponents. So, yeah.
So you just multiply by the, for 1, you get 1 form of 1 by just the highest power.
Yeah, yeah, and so the highest power was x to the negative 3, so we multiplied by x cubed, so those things would cancel out. We wouldn't have any more negative exponents. And that's generally the case when you have negative exponents involved, particularly when they're in a denominator like that. Yeah, so this antiderivative here, let me see, I think I'm going to add a new page in your notes. So we had, was it x over x squared plus 1? And this is more or less what you're doing with those u substitutions where you just have to move a constant. This is what you're doing in your head, maybe. But we see that the derivative of x squared plus 1 is 2x. We see just the x up there. So, you know, wouldn't it be nice if this were 2x? That way the derivative of this thing is right here. Well, if we want that to be a 2 out here, then we have to have this as a 1/2 out here. That way we're multiplying our function again by 1. And what we're doing is we're just forcing that to be in what we saw as logarithmic form already, right? So if you remember that when we take, well, let's start off, the derivative of the natural log of some, u is a function of x. It's 1 over u of x times the derivative of u of x, right? So what that leads us to is that if I take the antiderivative of both of these, and the antiderivative of u prime over u is equal to the derivative and the antiderivative undo each other. We're a little bit sloppy, but that's pretty much the main idea. If you've got a function's derivative over the function, it's natural log, it's logarithmic. So here's the function under its derivative. This is in logarithmic form because this is u prime. Does everybody see that? So our 1/2 stays out as 1/2, but this is just ln of the denominator. I mean, it's really this here, but we've got derivative over function. The antiderivative is always the natural log absolute value of that denominator. So here's another example. If we had to find the antiderivative of 9x squared minus 4x plus 1 all over 3x cubed minus 2x squared plus x plus 4 with respect to x. And if this pattern seems weird to you, then just forget about it, because this is what we're talking about here, is being able to recognize this pattern into a much more efficient antiderivative. But if it's weird, then just do a u substitution. It'll just involve a couple of more steps. But there's nothing saying that you have to know this or have to do this. It's just like if we know those formulas on the first page, it's a lot more efficient to know those as opposed to doing a u substitution as well. Right.
Because that's the derivative on top and the
Right.
derivative on the bottom.
The function here, we see that function's derivative is right here. So this will evaluate to what?
Natural log of the denominator.
Yeah. Natural log of absolute value of the denominator. Again, if you don't recognize that, then you're going to have to do a u substitution. It's just a couple of steps removed, that's it. What about the antiderivative of 4e to the 2x plus 4x cubed over 2e to the 2x plus x to the 4th? Is that in log form? Yeah. So the denominator's derivative is up here, right? Here we could drop absolute value because that quantity is always positive, but it's just more important to recognize the pattern. Does anyone have any questions on that?
And you're saying we can manipulate what's in there by a constant, as long
Right.
as it equals 1, to try and help push it to that
Yeah,
balances stuff.
yeah, exactly. So here's like another example. Yeah, Rich.
I was just gonna say, just to confirm, you can only do it by constants, no factor of x. Just constants.
Just constants. Yeah, they differ by a constant. So you might remember that we've only seen the derivative for sine, the antiderivative for sine, the antiderivative for cosine, and that's it, right? We haven't looked at what's the antiderivative of the other four trig functions? What's the antiderivative of secant, cosecant, cotangent, and tangent?
Like it's cosecant squared.
Isn't that like ln down?
Well, that's cotangent squared.
ln sine of x.
Yeah. So if we view cotangent as cosine over sine, then this log form, or which is just u substitution, is evident. So the derivative of sine is cosine. Right, so what would this integral be?
I want ln sine of x.
Yeah, ln absolute sine x. Yeah. I mean, so honestly, you could have talked about this after you've done u substitution. For whatever reason, our calc textbook doesn't introduce it until 8.3. So we will see these again in 8.3, but know that you can do them now. Another example, the antiderivative of tangent. Same idea, write that as sine over cosine. Derivative of cosine is negative sine. So we need a negative here for that to be in log form. But if I'm going to put a negative there, I have to put a negative here, right? I'm multiplying by positive 1. So what would this evaluate to? All right, negative ln absolute value of cosine of x, which is ln absolute value of cosine to the negative 1, and the reciprocal of cosine is secant. And generally that's how you see this antiderivative presented. And if you, again, try u substitution on any of these, you see that it works exactly the same way. It's just sort of a way to bypass u substitution, just like the ones on the first page. If you just remember that, you're bypassing u substitution. If it's weird, just remember u substitution then. Do y'all have any questions on this? Yeah, Dave.
Where did that negative sign go? Negative ln absolute cosine x, and then the next.
So remember, properties of logarithms, the negative 1 is up here now as a power. So that's reciprocal of cosine. Any other questions? Okay. So it was a detour, but I think it was worth it. Okay, how about antiderivative sine cubed over cosine to the 5th?
Change that. Tangent cubed. Secant squared.
Okay, so the suggestion was rewrite this as sine cubed over cosine cubed times 1 over cosine squared. So we can write this as tangent cubed. Yes. Tangent cubed times secant squared. Totally valid to do that. Doesn't help, right? That's always the question with antiderivatives. What I do, does that help?
So did you split the top like the side times 1 minus cosine 2x over smooth?
Yeah, yeah, so we could say the top, we could also say that that's sine times sine squared. So that's sine times, 1 minus cosine squared.
No cosine.
Or what were you thinking?
I was thinking of 1 minus cosine 2x over 2. That's like the other item.
Oh, yeah, so that's also sine squared. Suppose we could do that as well. Let's stick with this. Is that helpful to write a tangent cube secant squared? Is one function's derivative sitting there?
Yes.
Yeah.
Yeah, tangent's derivative is secant squared, right?
1/4 tangent.
Okay, so that's it. U is equal to tangent du secant squared dx. So it actually turns into a pretty easy. Tangent to the third is now u to the third du for secant squared dx. So that's u to the fourth over 4 plus c, which is tangent to the fourth over 4 plus c. See, and honestly, they're just trying to be tricky. I don't know why anyone would ever want to write tangent cube secant squared for this kind of process, I guess, as opposed to sine cubed over cosine to the fifth. I mean, it's just doesn't make sense to write it that way. It's just they wrote it that way because it's a little bit more tricky.
Makes it.
Yeah, makes you think. Okay. So I mean, perhaps another like utilization of another identity could work, but you know, when we start utilizing these other identities, then we've got a lot more complicated functions that we're introducing, because it doesn't get much simpler than sines and cosines. Another common technique is when you have a bunch of things divided by a single term. Generally, the approach there is to just split them up. So if you have something like this, we can write this as 4 over e to the 3x dx. Plus the antiderivative of e to the negative 2x over e to the 3x. And oftentimes that can help us simplify and integrate. So this is for antiderivative of, can we do the antiderivative of 1 over e to the 3x?
Just negative 1 over negative 1/3 is equal.
Yeah. So we can write 1 over e to the 3x how?
E to the 3x on top.
Yeah, but if it's on top, then what do we got to do?
Negative.
Yeah. Right. So we can find the antiderivative of that. Here we just have to simplify. What's e to the negative 2x divided by e to the 3x?
E to the negative 5.
Yeah. E to the negative 5x. And so both of those we can do pretty simply. So antiderivative of e to the negative 3x is what?
-3.
Okay, good. Negative 3 e to the negative 3x. And then antiderivative here, negative 5 e to the negative 5x.
But wouldn't that be 1/5?
Oh, right, right. We're thinking of derivative here.
end up being 4/3, correct?
Yeah.
I think it was that.
So yeah, derivative we multiply, antiderivative we divide. So a similar approach as to example 1 would also work here. Like if we took our 4e to the negative 2x over e to the 3x and multiplied everything by e to the 2x. We've got a similar thing here. So we could also do that, but at some point you need to recognize, well, I've got multiple things over a single thing. Now split these two things up and simplify. So this route would also work. It's not always clear cut as to how many different strategies would actually work on a particular problem.
Could you multiply by e to the negative 3x over e to the negative 3x?
Yeah, we could also multiply it by e to the negative 3x. So that this might be even a bit more efficient, because that would make our denominator 1 and we wouldn't even have a denominator there. So yeah, certainly can do that. Any other questions on that? All right, this is again improper. We've got degree in the numerator is larger than or equal to the degree in the denominator. So we're going to first divide this. So let's see if we can all divide this.
negative 6 times x is negative 6x. And then, wait, what am I doing? Right, but then what I do is I multiply by negative 1. And then that way I can get positives. And I add that.
What'd y'all get?
I get rid of yeah.
X minus 2 plus 12 with a remainder of 12.
Say that again?
X minus 2 with a remainder of 12. It's been a while now.
Well, thanks for your bravery. Appreciate it. Anybody get anything different?
Yep.
Yeah, long division.
So is it, can I ask you if I got the right answer?
Yeah, what is it?
X minus 6 plus x plus 6 over 40? Either way.
Yeah, that sounds close.
Close.
Yeah. So it's just based off this leading term right here.
Just x minus 6 with a remainder of 6.
X goes into x squared how many times? When we multiply, x times x is x squared. X times 6 is 6x. And then we subtract that quantity.
Got that far.
We have x squared minus x squared, 0, 4, minus 6x. Start over, x goes into negative 6. How many times? 6x rather. Yeah, negative 6 times. Multiply negative 6 by x, negative 6x. Negative 6 times 6, negative 36. Subtract off the quantity. 0, we have 4 plus 36, which is 40. So your result is x minus 6, remainder 40. We put the 40, the remainder, over the divisor. Because remember, we're expressing x squared plus 4 over x plus 6. Or re-expressing, rather. Do what?
Long division. Much easier than this.
Yeah, right. So it's now a much easier thing to work with. Do we know the antiderivative of all three of these? Yeah, so let's write this. Antiderivative of x minus 6, for sure we know that. Plus 40. Antiderivative 1 over x plus 6 dx. We have x squared over 2 minus 6x plus 40. What's the antiderivative of 1 over x plus 6?
ln x plus 6.
Right. So that's already in log form, natural log. Absolute value of x plus 6. So the derivative of x plus 6 is 1. This is already in log form. If you can't see that, fine, then you just use a u substitution there on that third antiderivative. We can see immediately with this one, when we take its derivative, we get x minus 6 plus 40 over x plus 6. And there we just find a common denominator, and we're back up to x squared plus 4 over x plus 6.
And you're fine with us leaving the absolute value on the x plus 6 expression, right?
Yeah, you have to unless you know where that x plus 6 is. It's sort of, when we do that, it broadens the range of what x values can be here. Because normally we would just say, well, this antiderivative is the ln of x plus 6, but none of that could be negative. When we put the absolute value, all we're doing is we're kind of expanding that so that we can have the absolute, or the natural log rather, of both positive and negative numbers, excluding when this quantity is 0. Still can't do the natural log of 0. Because the derivative is the same. If I look at it the other way around, the derivative of the natural log of the absolute value of x is still 1 over x. Any other questions? All right, let's see. I think that, yeah, the final technique that we can use is completing the square. So completing the square on x squared plus 4x plus 8. Do y'all remember the process to do that?
Isn't it
Maybe.
4x over 2 squared?
It's it's 4 over 2, and then we square that value and add it to both sides. So you take this number and kind of scoot it over. Take half of 4, which is 2, square that, add it here. So that's now a square. But if we add in 4 to the expression, what do we have to do? Yeah, subtract 4. So we're adding in 0 in a special way to complete the square. This is now x plus 2 quantity squared. Oops. And that's positive 4. Okay, so that's completed the square in the denominator. Is that helpful? I mean, it kind of it kind of looks like this would be, if it were just 1 over this, then that would be an arctangent of x plus 2 over 2. But we've got that other x hanging out, so.
Pesky X.
So this one's not as straightforward as I think some of the others. Maybe that's a relative expression.
Now I can multiply it by a factor of 1.
So if we would have to multiply in order to like get rid of this, or to get rid of this. Yeah, I don't think we could get rid of either. We could divide by 4, but then we would have this over 4, this over 4. This to the negative 2 would still make this x plus, what would that, x plus 2. So that'd be 1, 4x to the negative 2, x to the negative 1. So it's getting a little more complicated if we do that.
Could you split it up, common denominator, or? Oh, no, never mind.
Okay, so let's try this. Can we do u as x plus 2? Du is dx. So we account for this here, the plus 4 is fine. If we had u squared plus 4 on the bottom, again, that's fine. We should recognize that as an arctangent. But what about the x? What is x?
U minus.
Yeah, x is u minus 2. If u is x plus 2, then u minus 2 is equal to x. So let's see. I mean, it doesn't look that much different, right?
That's log.
Well, it's not quite logarithmic, because the derivative here on the bottom is 2u. The thing up top is u minus 2. I mean, we could put a 2 right here against the u, but that means we're also multiplying this here. So we'd have a 2u minus 4 with a 1/2 out here. So it's that, if it were just u, then yeah, that's fine. But it's that u minus 2 that's,
Can't put 1 as the leader in.
yeah, right.
So can you just split it up?
Yeah, this one's actually better than this one here because this one, with the u's, we can split that up into two separate integrals. So that's going to be the antiderivative of u all over the denominator minus the antiderivative of 2 all over that denominator.
So that second one you can handle over the first one.
Do what?
Wait, no, you can't handle it, though. Never mind. Yeah.
So the advantage of doing that, the first one, is that in logarithmic form?
Yeah.
Yeah, but we need a 2 here. So we need a 1/2 here. Now that's in log form. In other words, that one you can use a u substitution on that first integral if you don't put the 2 and the 1/2 there. Log form for that one. What about the second one?
That's the arctan.
That's the arctangent. So we've got our 1/2 here times the natural log, absolute value of u squared plus 4. For the first antiderivative, do y'all agree?
Yeah.
Minus, what's the antiderivative of 2 over u squared plus 4 du?
2 arctan u.
Close. So it's 2 times, this is the inverse tangent of what? Not of u either.
Over 2.
Maybe look at that first page. Get back to that first page. Okay, and what else?
2 plus c.
Well, plus c, yeah.
Well, C's gonna be at the end of everything.
Just look at that first page.
It's cheating.
U is our variable, 4 is our a squared.
So plus 36.
You think it was 1 over u?
Yeah, it's got to be 1 over
1 over u.
a inverse tangent of u over a. What's a?
4 or 2.
2. So it's 1 over 2 inverse tangent of u over 2. The only ones that don't have the 1 over a as a part of their, multiplying the constant here are the inverse sine and inverse cosine. All of those other functions have that 1 over a as a part of the reversing the derivative. We'll just put a c in at the end. So whatever we get here, we'll keep our constant out here. Okay. So there's the 2 from this 2. The antiderivative of 1 over u squared plus 4 is this right here. Are there any questions?
The ln, can we get rid of the absolute value for that? Is that?
Yeah. So remember, in terms of u, you could get rid of this, but you've got to resubstitute in for x. Right? Because this is really an expression involving x. So we want to make sure that whenever we resubstitute for x, that this quantity does indeed always stay positive before we remove the absolute value. So we'll see what that looks like once we resubstitute. X plus 2. So let's just leave that here for now. And this is x plus 2. U squared plus 4. Is that quantity always positive? Yeah, you've got a square plus another number that's always positive. So we don't need the absolute value here. And then we have minus the inverse tangent of x plus 2 over 2. Plus.
Like, explain how you got that 1/2 u over 2.
1/2 u over 2.
It's from
Yeah, I mean, if you look at number 12 on the table, on the first page, that's how it goes. The only other way to really show that is if we take the derivative of that. So if we take the derivative of the inverse tangent of u over 2 with respect to u, then we can justify that integral formula, but that's really about the only way we can show it. We talk about the derivative, and then we undo that thing to get an antiderivative formula. So this is everyone okay with this? This is just like 2 times the antiderivative of 1 over x squared plus 2 squared dx. So that would be 2 times 1 over a inverse tangent of x over a. So I don't really know any other way to explain it. We could look at the derivative if we need to. Any other questions on that? So you really do need to know number 11 and number 12. They do show up. From this point on, they're quite common. Okay, that's 8.1. If you're, like I said, if you're interested, 8.6 has some more kind of general approaches to taking the antiderivative. But by and large, I think it's hard enough to remember all of the what do you call them? All of the tools that we're learning in this section. So on the exam, I will say, use this technique to find this antiderivative. That way it takes some of the pressure off, I guess. Because otherwise it can be really tedious. Any questions on 8.1, formerly known as 7.1? All right, let's take a break and then we'll start 8.2. Okay. Are y'all not ready?
I'm not ready.
Fair enough. So here in 8.2, we're going to look at the reverse of the product rule, which is called integration by parts. So we can establish the formula for integration by parts just like we establish any antiderivative formula. We start with the derivative of a function, and then we take the antiderivative of both sides and work through that. So that's what we're going to do here. We know the derivative of a product. Here's the product rule. And if we look at the antiderivative with respect to x on this side, we have to look at the antiderivative with respect to x on that side.
So it's an antiderivative of the derivative.
On the left-hand side, yeah, antiderivative of a derivative.
Yes.
We know that those are inverse operations. So what we end up with here is just u of x times v of x equals to the antiderivative of u prime v with respect to x plus the antiderivative of v prime u with respect to x. Okay, a couple of things to note here. We're going to write u prime of x as the derivative of u with respect to x, and v prime of x dv over dx. So what happens here, we have our differentials dx cancel out. Oops. And so what we're left with there for this integral is just the integral of v of x with respect to u plus the integral of u of x with respect to v. And that's still equivalent to uv. And since we know u and v are functions of x, we're going to drop that of x part and just say uv is the integral of v du plus the integral of u dv. But again, we just have to remember that this dv is actually dv over dx times dx. And the du is du over dx times dx. And then we'll solve for, traditionally just how it's presented, we'll solve for the integral of u dv and say uv minus the integral of v du is equal to the integral of u dv. I don't know, did I put the formula in there? So I didn't put the formula in there, the actual slide, but that's the formula we utilize when we integrate by parts. This is what we start with. This component or this piece is what we're given. So we're given, find the antiderivative of this, where this is a product of two functions. Remember, this is a function of x, u is a function of x, and dv is a function of x, right? dv was the derivative of v with respect to x. So I don't know why it's presented that way, but that's the way it's presented. And so when we're given this particular thing, you know, like find the antiderivative of x, e to the x with respect to x, what we have to do is we have to identify u and dv, because that's what we're given. We're given essentially u and dv. And then notice over here on this other side we have u, v, and v du. So if I identify u, I need a du over here. So once I identify u and dv, I take the derivative of u to get du. From dv, I take the antiderivative, because that's a derivative, I take the antiderivative of dv in order to get v. And then this integral that we end up with over here should be easier or the same as the original antiderivative you started with. So that's sort of the process. So the process of identifying u, I guess there's a few ways to think about it. Maybe we can think about it as we want to identify dv as the biggest portion of that integrand that we know how to differentiate. Or the way I've presented it here is this acronym. I don't know that it makes any sense, but if you can remember this acronym, it will allow us to remember what we should let u equal to. And if we know what u is, then we know what dv is. So there's a couple of ways to think about it. This is the way we're going to think about it. So it says dv should be easy to integrate. And what that translates to is the functions from left to right. Hard to integrate, easy to integrate. So the L is for the logarithms. The I is for inverse. Typically like inverse trig functions. A is for algebraic. Polynomials, like 1 over x squared, those types of things. Square roots. T is for your trig functions. And E for exponential. Typically in the form of e to the x or e to some power. So in this right here, this is our choice for u. So we're going to let u equal the leftmost function. So if I've got an integrand that involves logs and inverse trig functions, I'm going to let u equal log. If I've got an integrand that involves algebraic and exponential functions, I'm going to let u equal to my algebraic function. So let u equal the leftmost function in this acronym. And then that way we can also distinguish what dv has to be. Here. Always let u equal the leftmost letter or function in that acronym. So just 2 for practice. We're not going to compute these. We will at some point, but
U equal cosine of x and v equal to e.
right. So we're going to let u equal the cosine x. What 2 things do we have to choose? U and dv. So we choose u as cosine. That means dv is the rest. dv is e to the x dx. So you always start by picking u and dv. Based on those 2 choices, we have to find du and we have to find v. So the derivative of cosine is minus sine x dx. And the antiderivative of e to the x dx gives us v, and that's just e to the x.
Worry about a plus e.
No, we won't worry about the constants till
Okay.
we're through the process. Okay. So then from there, we just have to remember the formula. A mnemonic that's used to remember this formula, I don't know if it's useful or not, but this integration by parts, we have uv v du. So sometimes they call integration by parts ultraviolet voodoo. So I don't know if that's helpful or not, but. Okay, how about problem 2? What should u equal? Should it be sine x? Yeah, because x squared is our algebraic. This is algebraic. This is trigonometric. So we're going to let u equal x squared, which means dv is what? Yeah, sine x dx. The differentials include other differentials. So don't get sloppy with your notation. Don't say dv is sine of x, because then you're missing that piece dx that was in the original integral. All right? So that means du is the derivative of u, 2x dx, and v is the antiderivative of dv. So that's how we set that up, and then we do uv minus the integral of v du. Do y'all have any questions? Yeah.
Just clarifying, so u is supposed to be the leftmost in that mnemonic.
Yeah.
So we've got exponent there for u, and then dv we have trig.
Mm-hmm.
So wouldn't trig be the leftmost one? You'd make u equals sine x?
Well, it's liate. Where do we go with that? So we would want to make u the algebraic, and dv is the trig. So the leftmost is u.
Okay.
It means like if x is in the exponent.
Okay.
Oh yeah, did I misunderstand what you were asking, Tavis?
Yeah, that's fine.
Okay, sorry about that. Any other questions? Yeah, algebraic are like power functions. Exponential would be like 2 to the x instead of x squared. Okay, so let's evaluate x e to the x. So the telltale sign of when you know you have to use integration by parts, typically is when you've got two functions of x being multiplied. And remember, multiplication can be defined in terms of division. So this could be e to the x over x, and we could use integration by parts there as well. So we should let u equal to x, which means dv is, good, all right, e to the x dx.
Du just equal dx.
Du here is 1 dx, or just dx, yeah. So du is dx. V is the antiderivative, so e to the x. So built in as an intermediate step in this is derivatives and antiderivatives. Then you've got to fit all that together in the formula, which involves another antiderivative. So you really have to start keeping things straight. Otherwise, it's going to be really easy to mess this up. So our integration by parts, we take u times v. So x e to the x minus the integral of v du. So the second integral we end up with, we said should be easier or equivalent to the original. Definitely the antiderivative we have now is much easier than the original.
That's
Just take x e to the x dx, and you just leave the x e to the x.
Right. So that x e to the x is going to stay because there's nothing to do with that. But we can finish the antiderivative of e to the x. So that's x e to the x. Antiderivative of e to the x is e to the x. Let's see. Do y'all have any questions on that? All right, y'all try this is number 2, x cosine x.
Oh, no, I figured it out last semester, yeah.
Oh, really?
I made sure I got knowledge on every single homework, and I put like 90s, just like average.
Oh, right.
Yeah.
And then
But
like
you-
by context,
Right.
it's still.
Yeah, I actually haven't seen it. It works out that way.
It just took the stress off of the test so that I like, when I sat down, I didn't have to.
Right. I agree. Except for those quizzes.
What'd y'all get?
X sine of x plus cosine of x.
Okay, good. Yeah. U is our x algebraic function. dv is our trig function, cosine x dx. Derivative of u is dx. Antiderivative of dv is sine x.
Oh,
You guys are still working.
Oh, wait, wait,
I don't know, call that C1. So x sine x plus cosine x.
now I understand. Now I
That's other stuff. Okay.
Do y'all have any questions on that? Cool. Okay. So antiderivative of x ln of x. What should u be?
You should be.
Ln of x logarithm makes dv x dx. Derivative of u is 1 over x dx. And the antiderivative of dv, antiderivative of x, is x squared over 2. Most of the time it's really straightforward when you use integration by parts, because we see all of these are just a product of two functions of x. Sometimes it's more subtle, but usually pretty straightforward. So we have u times v, which is x squared over 2 times ln x, minus the integral of v du. So let's just simplify that before we plug that in. We have x squared over 2 times 1 over x. So we have x over 2. We'll put that 1/2 out here. So that's our x over 2 dx. Is everybody okay with that?
Why is it just x?
Because we've got an x squared divided by this x. So v, the integral of v du. We've got x squared over 2 ln x. We have x squared over 2 times negative 1/2. That's negative 1/4 x squared. Do you have any questions? And yes, you can do integration by parts more than once. So example would be x squared cosine x. The more times you do this, the more careful you have to be, particularly because of this minus the integral of v du part. So if I do integration by parts twice, then this integral again is going to get broken up into another uv minus the integral of v du. So you just got to be careful with that sign that was already hanging out front if we do this multiple times. Okay, so u is going to be x squared dv cosine x dx. Du is 2x dx, and v, that is sine x. Okay, so one iteration of integration by parts. We have the integral of x squared cosine x dx is u times v, so x squared sine x minus the integral of v du. So let's put the 2 out here, x sine x dx. Yeah.
Wouldn't dv be sine x? Because it's the derivative of cosine x?
Antiderivative to go from dv to v. Yeah.
Wait, so you can pull out that 2? I thought it'd be indirect become 2x.
Yeah, totally. It would be the minus the integral of 2x sine x dx. And then we could start over with this and say, well, now our u is 2x, right? Or since it's a constant of integration, we could leave it out. It's really just a matter of preference. Would y'all prefer to leave it in or factor it out?
Take it out.
Take it out. So again, another thing to be mindful of, if you're taking out constants of integration, this is going to be minus 2, and we're going to split this integral up into another uv minus the integral of v du. So you got to remember that constant we take out is affecting both uv and the integral of v du. But there's nothing wrong with taking it out as long as you can keep it where it needs to be. Also, nothing wrong with leaving it in and having that 2x be your new u. There's, either way is fine. So the idea is we had an x squared times a trig function, and we've broken that down into now we've got a x to the first times another trig function. So we've effectively reduced the power on x once, and then so another round of integration by parts here should eliminate the product. So it's probably, it's not technically sound to have another u and another dv, because we already allowed u and dv to be something else. But I think just to avoid confusion, you know, like we should let's just keep this notation. Really, we should let that be, you know, like w and ds or something like that. But for our purposes, I think it's fine. All right, so in the new integral, u is x, dv is sine x dx. Derivative of u, excuse me, is dx. Antiderivative of v minus cosine. We have our x squared sine x minus 2 times all of this stuff v minus x cosine x minus the integral of v du. So I would just recommend that you plug everything in as it is, and then you can start reconciling the signs or the constants. Otherwise, you're bound to miss something if you don't just fit it in. Do y'all have any questions on where we're at? So we have a positive 2x cosine x. We have this right here. We can reconcile these negatives if we want. This is negative 1 times this, so that's now plus the integral of cosine x. But again, all of that's times that negative 2 that we pulled out. So minus 2 times the integral of cosine x dx. So I don't know, you might find it easier to leave the constants of integration in and just consider those part of, you know, your algebraic or your trig or whatever. Nonetheless, we now have something we can finish antiderivative for. So the antiderivative of cosine will complete this. Oops. With all of this stuff. Do y'all have any questions on this? All right. There's actually a more efficient method to do this. It's really like tucked away in your textbook in the exercises. I think we should do one more of these before I show you that. So why don't you all try example number 5.
Oh, I got this
Multiply that by 2x, it's minus a negative.
The second we're talking about right here. So when we set it up, negative x equals negative x, I made this positive.
The second piece should be positive because it's the integral x squared to get to the negative. It would have to be positive right here.
Oh, I see what you did. See, I pulled that out. I pulled the 2 and the negative.
So for this to be a nice it's like it would so the u here
So that second one is
positive. Yeah. But then I find that I screw stuff up and I start pulling stuff out. So I just try to
I know.
where you screw try to check
Except I need like
x squared e to the negative x.
Yeah, 2 hours
Okay, but it's still have each to the negative. Pretty much.
Like I bunked them for college algebra, and then I got really frustrated with just a couple of them in pre-calc, and then last semester I was I really don't like the smart book stuff.
So did you oh, because if you didn't, yeah, if you didn't, you would have to
So dv is necessarily take the antiderivative here.
Leslie, the second day about it, just got
Explain the dv.
And then it's like, I'm so past the email, I don't even want to like make you try it. He's like, no.
Constantly have to like choose the returns, make sure it's
Are those the
They're really nice. They're both like 14 or something. Yeah, I know. And
they're very, very tasty.
I didn't know they were brothers because one of them has
You didn't?
one of them has
You couldn't tell?
well, I was like, okay, definitely was returning you very really safe. And because they're kind of like matching everything like that.
They're still not. Are they like legitimately 14?
I think they're like probably like 16 or something. I don't know. They look really from high school. They have like matching calculators. They have a matching water bottle.
I mean, if I had 2 kids, I would just, I'd get that.
I mean,
if I had 2 boys, but
There was a girl in my chemistry class last semester who was a senior in high school, and she was in Calc 3 last semester. I was like, you make me wish I had this for so much when I
I
was
think if I did this like straight from high school, I mean, really lazy in high school, so I took supervised classes, so I never had to do any homework. I started off with APs, and then like first weekend I went to my advisor. I was like, let's just go normal track.
I remember my Spanish teacher sitting me down in my IG Spanish class and being like, you're not really going to go anywhere in life with this. She's got a negative.
I know it's the absolute value.
But I feel like if I
Actually, if you look around you, it's kind of stupid not to learn Spanish.
Oh, no, I agree. I know, my mom's taught me so
it's just the whole like grammatics.
I don't practice it. You drop me in the country and I'll get
Yeah. Also, there's just such a difference between like textbooks English and like actual Spanish.
Listen, I learned my Spanish in the restaurant I worked at. Everyone that's all the cooks, so that's where you learn your Spanish.
Yeah.
That's a good restaurant.
Yeah. my students were like, mixed. Alright, I'm sorry. I'm like, teach me that.
I think I just wrote this.
Really don't. Black out luck. I'm like, oh, excuse me. I didn't know that.
Oh, I didn't check with y'all. How are y'all?
I think we got it.
Yeah.
Yeah, we're doing construction for years. I've been 2 Venezuelans, and we just have full conversations by the end of the summer.
Oh, wow, that's awesome. It's a nice feeling.
My parents dropped me. And I thought we were going on vacation. They went somewhere else. They're like, you're going to live with this family. And I got to tell you, it was character building.
It helps if they don't speak English.
Oh, yeah. And mosquitoes. I lived in this mountain house that had holes just made out of concrete blocks. And mosquitoes. But I did. I can do this.
How long was that for?
It's for 2 weeks. Yeah, I took the bus on my own. I ordered a soda and a plastic bag. Yeah, I was walking around. I was like, Thursday for soda. 1 peso. No, actually, they use dollars there. So. Pretty cool place. Panama's wild. Wild place.
Sure helps if they don't speak English.
Yeah, I mean, it's like, yeah, that. Because you could like start pointing to things and like get some dialogue.
Yeah. Like you're teaching them, you're teaching them.
I heard the word Greek. Be patient.
Oh, yeah.
Okay, so most of y'all had the correct answer. I think what you encountered was the issue with keeping track of all of the signs when you have to do this multiple times, right? So you want to make sure it's not really that big of an error on an exam, but I mean, if this were like a real thing, the difference between a positive and negative, you know, you're on top of the building or you're below the earth, right? So it makes a huge difference if this were like a real thing. Okay, so then again, this right here and this right here will make those positive, and then we have a 2 times negative e to the negative x for this antiderivative. So negative e to the negative x there. This is 2x times negative e to the negative x. And this was already here. And you know, some of y'all did it different ways too, depending on if you took the constant, the 2 out, or if you just let u equal 2x. Some of you left it as a negative and let u equal 2x, then dv has to be negative e to the negative x. So there's a lot of ways to look at it. Find whichever method you prefer. I honestly prefer to just deal with constants as a separate thing, but you can totally leave them in if you want. Okay, so there's a faster way embedded in your exercises. This is another reason why looking at exercises can be beneficial, because oftentimes there's not enough time to like talk about all the techniques, and they'll hide certain formulas or techniques in the exercise, usually without consequence, but I think this tabular integration does have a pretty huge consequence. So it's mentioned as an exercise in this section, problem number 77. It's called tabular integration. It's basically just creating a table of u's and dv's and corresponding them in a correct way so that you don't have to do integration by parts over and over and over again. Okay. So here's the basic idea, and we'll look at those last two problems, x squared cosine and the e to the x one. So we start off with a function times another function, f and g. The choice for u is f, and the choice for dv is g. So along this column here, we have our choice for u and all of its derivatives. This column g and all of its antiderivatives. We then have to correspond them in a certain way. When we move across, we're multiplying those two functions together. When we move horizontally, we have the integral of those two functions multiplied together. Okay? The other caveat here is that as we change as we change columns, we start with plus and then we alternate the signs, plus minus. See, this one's plus minus plus. If we had a fourth column, or fourth row rather, it'd be minus, plus minus, plus minus. You just have to alternate it that way. That's due to the negative built into our integration by parts right there. Okay, so let's see how that actually works. I'll take a picture of this and put it in our notes in case you want to reference it. So what was this one? X squared e to the negative x.
What's it called again?
Tabular integration. So we're just making a table. Choices for u and dv are the same. So here are u and all of its derivatives. So our u was x squared. Here's dv and all of the antiderivatives. So also remember to alternate these signs. So this first one's positive, the next one's going to be negative, and positive, then negative, and so on. This one will actually end because we know we eventually reach a zero derivative for power functions. So derivative 2x, derivative 2, derivative 0. So that's where we would stop. Antiderivative, negative e to the negative x, antiderivative again, e to the negative x, and antiderivative again, negative e to the negative x. So that's basically our table, and we have to crisscross. So we have a positive x squared times a negative e to the negative x. Then we have a negative 2x times e to the negative x. And then finally, our 2 times negative e to the negative x. And since this was 0, there's nothing here that corresponds to 0. We wouldn't, it's 0 times whatever is 0, so.
Wait, so just go down the road, like move myself across.
Yeah, so down is derivative, antiderivative, but then we have to move adjacent or diagonally to get those products. So that's a product, that's a product, that's a product.
We wouldn't stop at the 2 and e to the negative x and then go across.
Well, so remember, if we go, across from here to here, you mean like across this way?
Yeah.
that?
We're skipping that step by doing another.
Right.
Okay.
If we were to go across here, whenever you move horizontally, you have the product, but it's an antiderivative. So if I moved horizontally, I would say that this is a positive 2 times e to the negative x, but since I'm moving horizontally, it's this right here.
So by doing that other diagonal,
Yeah.
you skip that.
Right. Doing this other diagonal, the purple, gives us the antiderivative of this right here, negative 2 e to the negative x. Right. Or if I didn't want to stop there, technically the next thing that's left over is that final step to correspond 0 with the e to the negative x. But again, if I move horizontally, I have to take their product and the antiderivative. So I would have minus the integral of 0 times e to the negative x, right? Well, that's just 0 anyway, so there's no need to mess with that. Yeah.
And as you're going down, you always subtract, right?
What do you mean as we're going
Well,
down?
I'm saying because you have x squared times negative e to the negative x, and then your next would be minus whatever your next expression is, which is going to be 2x x.
Oh, yeah, yeah.
Okay, so it's always, you always,
Yeah, so we've already used those two. Then we have to move down next to use that one. So yeah,
Well, they're always gonna be added as subtracts.
right. In effect, those functions have been crossed out.
So as long as we follow the derivatives down to 0, we don't have to do a horizontal multiplication and then integration?
Right. Yeah. If you follow the derivative down to 0, none of the horizontal integral thing. But the problem is that not all functions reach a 0 derivative, right? So at some point, you might have to utilize moving horizontally and taking the antiderivative of that product. Yeah.
So if U doesn't go to 0, you can't use this one. Like if it's like the trig function, instead of monoid function, you can't use this one.
So it'll be like, you can use it, so the one y'all were looking at or working where it was e to the x cosine,
Yeah.
you would just have to stop when you have the same integral. So like you would have a e to the x and a cosine right here. You would have to stop there and then combine the antiderivatives that way.
This basically works if you have an algebraic function.
No, this works. So here, so our textbook, it just says, well, does it specify? Yeah. So the criteria on f and g, it just says f can be differentiated repeatedly, and g can be integrated repeatedly. So this example we saw, I mean, I wouldn't consider that we're differentiating that repeatedly because eventually it reaches 0, but it still works. Okay, so let's go back to that other one. We had this one, x squared cosine x. And a similar thing here, we'll have our u's and our dv's. So u was x squared, derivative 2x, derivative 2, derivative 0. And then don't forget to alternate the signs. We start with the first row positive, second row negative, positive, negative, and so forth. dv was cosine, antiderivative is a sine, antiderivative minus cosine, antiderivative again, sine. Yeah? Okay, when I start with the first u and move diagonally, those two functions are now used up. That's the product. So it's x squared sine x. Move diagonally again, starting with a negative 2x times a negative cosine. Gives us a positive 2x cosine x. And then finally, the 2 times the negative sine. So negative 2 sine x plus c, whatever. So that's, you say that's the same exact result. I just want to point out though, like sometimes you need to do this. We could say that it's x squared, positive x squared times sine x. And then if I want to move horizontally here, sine x and the negative 2x, then I would have to say that that's minus the integral of 2x sine x dx. So we see that makes total sense because the integral of 2x sine x gave us these two terms here, right? So there's layers and how we want to stop, or where we want to stop rather, really depends on the function that you're dealing with, the product actually. I mean, even if we go back to the first example that we looked at, where I think it was x e to the x or something like that. Maybe not. Yeah, x e to the x. It still works here too. So you can try it for yourself if you want. But does anyone have any questions on that? hidden gem.
So for the one above, on the thirds, you wouldn't integrate 2 minus cosine x.
Say that again here.
So it's not that you did negative 2 of x, sine of x. If you go horizontal,
Yeah.
you do the integration of that one.
Yeah.
Nothing lying below.
I mean, we could, because remember this one and another, let's go back up here. This 2x sine x, 2x sine x, that broke up into 2 more things, a product and an integral, right? So, where was that? Right here. That broke up into these 2 things.
Oh, I see.
So when we look at it, yeah, we could keep going.
I hear you.
So if we did this product and then this product, we would then have this integral left over. Okay, so some of y'all that were working ahead, we're not going to do those last 2 examples, so sorry to let you down. But nothing like that shows up in your homework, so I don't think it's worth mentioning. I'll just reference the tabular integration came from example 77 and 8.2. All right, with integration by parts, now we can talk about what's the antiderivative of the natural log. So we've looked at the derivative of the natural log, which was 1 over x, but how do we find the antiderivative of the natural log? So just think of this as one function, which is the ln of x, times the other function, which is 1 dx. So what should our u be? Okay, the logarithmic function ln, which means dv, the only choice for dv is dx. There's nothing wrong with that. That's still a function of x that's 1 times dx. So du, that gives us 1 over x. And then the antiderivative of dx, antiderivative of dx gives us v. Yeah, so v is x. Derivative of x is with respect to v. Or derivative of v with respect to x is 1 dx. So that tells us that the integral of the natural log is u times v, x ln x, minus the integral of v du. Sorry, I forgot my dx here. Minus the integral of v du. Well, x over x is 1, so we're just integrating again dx, which is x. So that's x ln of x minus x plus c. So there's the antiderivative of the natural log. Sometimes that's the case, like if we want to know the antiderivative of like an inverse trig function, we have the same process. U is the inverse trig function, dv is dx, and we go from there. Do y'all have any questions at this point? Huh? Yeah.